Okay, in 5.6, we're going to determine the concavity of a graph and the intervals of the different concavities. Remember from last chapter, if something's concave up, it looks like this, kind of like a smiley face. The thing to keep in mind for concave up is that if it's concave up, f double prime of x is actually going to be greater than 0, or we consider f prime is increasing. And we'll stare at this to see why. Okay, so if I look at up here, the slope is pretty steeply negative. If I come here, it's still negative, but not as negative. A little bit less negative, and then here it becomes 0. And then it starts being positive, positive, and then pretty positive. So f prime is increasing. It starts out super negative, hits 0, and then it starts becoming positive. Okay, if the graph is concave down, it looks like a sad face. Okay, in this case, f double prime of x is less than 0, and that's because f prime is decreasing. Okay, and if you look at the graph, we'll think about why. The slope here is pretty steep positive. Becomes a little bit flatter positive, and now it hits 0. And now it starts becoming negative, and then it becomes more and more negative. So it started with pretty positive to pretty negative. So f prime is decreasing. It was super positive, now it's becoming super negative. Okay, we're going to try to find the points of inflection. Points of inflection are where the concavity is changing. So let me try to draw a graph. So if I drew something like this. Okay, over here I see that it's concave up. Over here I see that it's concave down, concave up. Okay, the point where the concavity is changing is the point of inflection. So in this case, maybe around here, that would be the point of inflection, because that's where the concavity changed from concave down to concave up. So for this first example, we're going to find the intervals of concavity for this function. So we're going to figure out when is this concave up and when is this concave down. What we want to check for is we want to see when f double prime of x is switching from positive to negative or from negative to positive, because that'll mean it's switching from concave up to concave down or vice versa. So let me go ahead and I'm going to find the first derivative. Bring down the 4, 1 fourth of 4 is 1. So x to the third minus 12x plus 1. But since this is concavity, I'm going to do the second derivative. Okay, now I want to determine whether the points of inflection are going to be where the concavity is changing from positive to negative. So just like with the critical points, I'm going to see when f double prime is equal to 0 or when f double prime is undefined. For this function, there's no values at which it's undefined, but there are values when it equals to 0. Okay, so x equals -2 and x equals +2 are my candidates as points of inflection, but I don't know for sure they're going to be points of inflection. That the sign has to change for the second derivative. If they don't change, then it's none of the above. Okay, now you can do a table or you can do the number line, depending on what you preferred in the previous section. So the two candidates for points of inflection are -2 and 2. Because I'm checking for concavity, I'm going to check the second derivative sign. So if I pick a number lower than -2, like -3, and I plug it in the second derivative, 3 times 9, 27 minus 12, that's going to be positive for f double prime. If I pick a number between -2 and 2, let's go with 0. 0 minus 12 is negative. And if I pick a number higher than 2, like 3 times 9, 27 minus 12, I'm going to get positive again. Okay, so if I look at this, since this is positive, this is concave up. This is negative, concave down, concave up. which means that, are they asking about my, no, they don't care about my points of inflection. I care about them, though. Okay, so anyway, so it's concave up from negative infinity to negative 2, and then also from 2 to infinity, and then it is concave down from negative 2 to 2. Did they ask about my points of inflection? No, they don't care about my points of inflection. Okay, if this had been positive and positive, then it wouldn't be, those wouldn't be points of inflection, but it would be concave up at those intervals. Should I tell you? Okay, I'm also going to write the reason next to it. It's concave up, and if they ask you why, because it didn't here, it would be because f double prime is greater than 0. If it's concave down, my justification is always going to be because f, second derivative of f, is less than 0. Okay, let's use some graphs to consider our points of inflection in our concavity. So, like always, be careful about what they've given you. In this case, they've given me f prime. Okay, I want to figure out the intervals of concavity and the points of inflection. When I look at concavity, I'm always looking for f double prime, or I'm looking for f prime to decrease or increase. Okay, so let's first consider where it's concave down. Okay, now if it's concave down, remember, f prime is decreasing because the second derivative is going to be negative. So I'm going to look at the graph of f prime, because that's all I've been given, and see where the graph is decreasing. So this is decreasing from x equals negative 4 to x equals negative 1. And then it's decreasing again from x equals 1 to x equals 2. Okay, now let's check when this is concave up. Because it has only given me the graph of f prime, I can only look at f prime and I can see when f prime is increasing. Okay, so where's f prime increasing? From x equals negative 1 to x equals 1. And then from 2 to 3. Okay, now what else is it asking me? It's asking for points of inflection. Okay, the points of inflection are the x values where the graph is going from concave up to concave down or vice versa. So this was concave down and then switched to concave up. So at x equals negative 1, there is a point of inflection. Okay, now it's concave up, switches to concave down, so at x equals 1. And then also right here, concave down, switching to concave up. Okay, now let's look at example 3. For example 3, they're giving us the second derivative. So if they give me this second derivative and I'm trying to check for concavity, let's see, if it's concave down again, since I have the graph for f second derivative, I'm going to see when f double prime is less than 0. So I'm just seeing when the graph is less than 0, which means that is true from negative 3 until we get to 1. And also from 3 until infinity. Okay, and if it asked me the reason, I would say because the second derivative of f is less than 0. Okay, let's look for concave up. Okay, and again, because I'm given the graph of f double prime, I'm going to only look at that. F double prime needs to be positive for it to be concave up, so that's going to be from here to here. And then also from x equals 1 to x equals 3. Okay, now what else? Points of inflection. Okay, the points of inflection are when the graph switches from concave up to concave down or vice versa. So here it switched from concave up to concave down at x equals -3. And again here at x equals 1. And then one more time right here at x equals 3. So there's 3 points of inflection here. Okay, let's try one more example of when we might want to determine the concavity of a function. Okay, it says, does the line tangent to the graph of f of x equals x e to the negative x at x equals 1 lie above or below the graph of f and y? Okay, if you recall from the last chapter, whether it lied above or below the graph depended on if it was concave up or concave down. So let's figure out the concavity and then we'll determine which way it is. Okay, so for concavity, I want the second derivative. Let me find the first derivative first. We're doing product rule. Okay, first, the derivative of e to the negative x is e to the negative x times -1 because of the chain rule, plus e to the negative x times 1 let's factor out the e to the negative x. Negative x plus 1. You can also leave it distributed. It's up to you. I need to do the second derivative, so I felt like leaving it as a product might make it a teeny bit easier for me, but we'll see. Okay, because of I took out the e to the negative x, I'm going to use the product rule now. So I'm going to do e to the negative x times the derivative of negative x plus 1, -1 plus negative x plus 1, times the derivative of e to the negative x, which is e to the negative x times -1 because of the derivative of the exponent. Okay, now where am I trying to evaluate this at anyways? See, I'm going to plug in x as 1, so I don't think I'm going to simplify it. Let me just try to plug it in and see how bad it is. So this is e to the -1 times -1 plus -1 plus 1 is 0. Oh, wonderful. Is 0. -1 plus 1 is 0. So 0 times all this is just going to be 0. Which means, let me write this. This is -1 over e. Well, that's definitely less than 0. So since the second derivative is negative, this graph is concave down. So let me reread the question. Does the line tangent to the graph of f of x at x equals 1 lie above or below the graph and y? Okay, so let me imagine this is a concave down graph, even though I have no idea what it looks like. If I drew a tangent line to the graph, the line is always above the graph. So let's go ahead and answer the question. Does the line tangent to the graph lie above or below the graph? Above the line. No, above the graph. Because f is concave down at x equals 1. And how did we know that? Because f double prime of 1 was less than 0. I'm going to say at x equals 1. Okay.